4.2, we're asked to solve trigonometric equations. This first one, find all real numbers that satisfy the equation sine x equals negative square root 3 over 2. Well, first off, we can talk about where sine negative. Sine is negative in quadrant 3 and quadrant 4. That's from our knowledge of all students take calculus. We're looking for where sine is negative. All of them are positive. Here sine is positive. So here sine is negative, here sine is negative. Because here only tangent's positive and here only cosine's positive. So these are our answers. Now, when is sine square root of 3 over 2? The answer is pi thirds. So we have the fact that sine of pi thirds equals square root of 3 over 2. So that's our reference angle. That's this value right here, pi thirds. This is pi thirds. So we have to compute what this actual angle is, and that's pi plus pi thirds, 4 pi thirds. And this one is 2 pi minus pi thirds, which is 5 pi thirds. So those are our solutions, 4 pi thirds and 5 pi thirds. They are pi thirds reference angles in quadrant 3 and 4, where sine is negative. Now the issue, though, is the fact that it says all real numbers. Because this value is one answer, but so is this value. So is this value. So is this value, forever and ever and ever more. Now what I'm doing to go from this answer to one time around is just adding pi. 2 pi, sorry, I'm adding 2 pi one time around the circle. So one answer would be 4 pi thirds plus 2k pi. And the other answer would be 5 pi thirds, and that one plus 2k pi as well. What 2k pi does is it adds so many times around the circle as whatever k is. K is an integer, so 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, 0, any integer for k. So if k equals 0, and this is gone, and we just get the 5 pi thirds. If k equals 1, we get 5 pi thirds plus 2 pi. We add one full circle around, we're back to another solution. There's an infinite number of solutions for trigonometric equations when they say find all real numbers. Because trig equations, trig functions have a period where they repeat themselves, and after that same period again they'll repeat themselves again. So we have infinite solutions to these equations. There will be some times when they say find all solutions within 0 to 2 pi, then they're specifying one time around the circle. Then you only get a finite number. But if they say all, you get an infinite number. And this is the most common approach to writing all solutions, this k pi or 2k pi or that type of version. We'll see a lot more of these. Next question. Now this question, wow, it is not correct. As I'm looking through this review, cosine plus, cosine always needs an angle, so I'm going to assume this is cosine x. So the right side is actually 8 cosine x plus 7 square root of 2. And the left side, 10 cosine x plus 8 square root of 2. This equation is very similar to algebra equations we've had. If I replace cosine x with like y, 10y plus 8 square root of 2 equals 8y plus 7 square root of 2. To solve for y, we just need to first combine like terms and get all the y's to one side. So although the cosine is in there, it makes it look confusing, but it actually is not. This is just going to be, let's subtract the 8 cosine x to both sides. And also subtract the 8 square root of 2. What we get out of this is closer to solving. We now have 10 cosine x minus 8 cosine x is 2 cosine x. 7 square root of 2 minus 8 square root of 2 is negative square root of 2. Divide by 2. We have cosine x equals negative square root 2 over 2. Now we're very close to our final answer. So if you don't just have a trig function equal a number, you'll have to do some basic algebra to solve to get there before you can go into the trig answer. Okay, where is cosine negative? Here and here. Because of all cosine's positive, students cosine's negative, take cosine's negative, and fourth quadrant cosine's positive. So we have two answers. One time around the circle. But again, this question is asking for all of them. So we will have at the k pi business on this problem as well. Now, where is cosine? We know that cosine of pi fourths equals square root of 2 over 2. So that's a reference angle. So that's this value right here and this value right here, pi fourths. So a third quadrant pi fourths is 3 pi fourths. Sorry, a second quadrant. A third quadrant is 5 pi fourths. If you wanted to add by pi fourths, they'd be here 1 pi fourth, 2 pi fourths, here's 3 pi fourths, and 4 pi fourths, and here's 5 pi fourths, 6, 7, and 8 pi fourths. 8 pi fourths is 2 pi. Now to generate all of these answers, we have to add, and notice you might think, well, why don't I just add 90 degrees and get this one? If I add 90 degrees once, I get another solution. But if I do a plus 90 degrees times k, then I get this solution, and then this solution, that's wrong, and then this solution, that's wrong. So I can't keep adding pi halves or 90 degrees and keep getting solutions. I would get these extraneous solutions, which I don't want. So I actually have to take this answer and add a whole 2 pi to it to get it again and again. Then go to this answer and add a whole 2 pi to it, etc. So this is going to be very similar to the last problem. Our answer is going to be 3 pi fourths plus 2k pi full time around the circle and 5 pi fourths plus 2k pi. Alright, next question. For this problem, it says round to the nearest tenth of a degree, so we're looking for degrees, but it says rounding. The reason why is because I don't know from the unit circle when tangent alpha equals negative 2.01. It's not one of the values that I recognize. So we're going to use our calculator. Make sure your calculator is in the degree mode because they're asking for degrees. To solve for alpha, alpha is going to be arctangent of negative 2.01. Understand where arctangent lives is either quadrant 1 or negative quadrant 1. In this case, because it's negative, our answer will be something there. That's what we're going to get out of arctangent. So you do arctangent of negative 2.01 in degree mode, and we get alpha is negative 63.549. Let's just go negative 63.5. Let me write it down, and then nearest degree, sorry, tenth of a degree, that gets us to negative 63.5. That's this value. It's negative, it's down, but notice it's also the reference angle. So we have the reference angle, negative 63.5. This is again asking for all angles. Almost every book I've ever seen, when they do the plus 2k pi type of solution, they use positive values. So what I want is, first off, where is tangent negative? Tangent negative here. Let's do this a different color. This one, and all students take calculus, and this one. So those are the two spots where tangent is negative. And the reference angle is the same. Now this means that we can actually get our solutions in nicer ways. But first let's figure out where it is. So to get this value, if I do 180 minus 63.5, I get 116.5. That's this value. If I do this one, this would be 360 minus 63.5. And that's 296.5. So the two positive answers. Our calculator gave us a negative answer, so we had to compute the positive answers. It didn't just give us any of the answers we needed. But again, our calculators are going to give you reference angles. That's up to you to get them into the appropriate spots. So we have these two values. So our solution, 116.5 degrees plus, how much do we have to add to get to the next one? Well, if we add 180, we'll get to 296.5. But does that pattern continue to be successful? If from there we add 180, good, we get another solution. And again and again. We can keep adding 180 from 116.5, so this would be 180 degrees K, and we'll get all of the solutions. You could also do it this way. Add a full 360 and do the 296.5 degrees plus a full 360. Okay. That's the two solutions. That's like taking this answer and adding a full circle and just continuing to get that answer, but missing this other one. So then come back over to this answer and add a full two circles, or full circle to that one. So you can get these two answers in two ways. One, by taking each one and adding 360K, and taking each one and adding 360K. But a more efficient method, by recognizing that these angles are off by 180, you can get all of them with just one recipe. Your book might have the K in front of the 180, so K 180 degrees instead of 180 degrees K. Though that's pretty small, it doesn't matter, they're both fine. Okay, next question. For this question, we are only looking for the solutions within the first circle. It does say approximate the solution to 4 decimal places, so we're back to our calculator. Notice, because of the pi in our equation, we need to be in radians. Alright. We actually don't need to approximate it, but we will anyway. So in radian mode, make sure your mode is in radians, do arc sine of 1/2. So arc sine of 1/2 is 0.5236. I have 5236. I have rounded to 4 decimal places. Where this is about right there. It's specifically pi 6. So you can check this. You can do pi divided by 6 and get that same answer. This is a unit circle value, but since they said approximate to 4 decimal places, I went straight to the calculator. Now, where is sine positive? Sine is positive here and also here. For 4 decimal places, we have our first answer. Our second answer would be pi minus the 0.5236. Now, although I have 0.5236 written down, On my calculator, I still have the 0.523598776, the unrounded one. I don't want to compute the minus 0.361. I want to do pi minus answer on my calculator, or pi minus all the whole digits. And it gives me 2.61799. So that would round to 2.6180. Now if I just do pi minus 0.5236, let's see if it gives us the same value. 0.5236. So pi minus 0.5236 is 2.61799. So it gives us the same value. I'm always worried that if I use a rounded value for the next part of my answer, it won't be rounded correctly anymore. In this case it worked, so that was nice. So we have 0.5236 comma, we have these two answers. Now we're only needing these two because they specified it. Our calculator gave us a reference angle, which is exactly one of them that we needed. To get the other one, we had to go pi minus there. And why pi again is because we're in radian mode. Otherwise I would have been in degrees and done 180 minus. All right, next question. For this question, we're asked to go twice around the circle. So from negative 360 to positive 360. Interesting. We also have our equation not solved for tangent. So we need to go through and solve for tangent. I will start by doing subtract 1 to both sides. This gives me square root of 3 tangent alpha equals negative 1. Then I can divide by square root of 3 to get tangent alpha equals minus 1 over square root of 3. So our calculator, do arctangent of minus 1 over square root of 3, and you get alpha equals, it's negative, and this is a unit circle value, 30 degrees, in degrees mode. Now why degrees? Because they have degrees in their question. Now what's important about this is the reference angle. Is 30 degrees. Let's take a look at, first off, we're looking for solutions in the negative 1 circle all the way to positive 1 circle around. And where is tangent negative? Well, knowing all students take calculus, we know that tangent is negative here, 30 degrees, here, 30 degrees. But there's actually 4 answers that we need, because we need negative, we need this answer, negative, this answer, negative. We also need, so that, let's work those two out. So that would be negative 30 degrees and negative 180 minus 30, 210 degrees. Those are those two answers. We also need the positive answers. We need this one and we need this one. Those are 150 degrees and 330 degrees. So with the reference angle 30 degrees, for the between negative 360 and 0, we have this answer, that's negative 30, and we have this answer. That's negative 180, and reference angle 30, negative 210. For the between 0 and 360, we have our first one is this one. That's 180 minus 30, that's 150. And we also have this one, which is 360 minus 30, 330. So we have 4 different answers. And that completes this question. Next question. Solve for x. All right. we just have to unwrap this present here. Let's divide by the 3. This gives us y over 3 equals tangent of 2x minus 1. Good so far. Let's unwrap the tangent with an arctangent. And we have arctangent of y over 3 equals 2x minus 1. Let's add the 1. I think I'm going to put 1 plus, because if it's on the right side, it's, I don't know, it's all good. 1 plus arctangent of y over 3 equals 2x. And finally, divide by 2. And to make this written nice, I might write it x equals 1/2 times 1 plus arctangent of y over 3. I will often change from divide by 2 to times by 1/2 when I already have a fraction in the problem. This looks like fraction over fraction. It's just a little messier. This is a little bit cleaner. The key to this takes it one step further. I don't necessarily think it's any better, but they distribute this 1/2 in to get 1/2 plus 1/2 arctangent of y over 3. Doesn't matter. I just leave it here. It's the first answer. It looks great. What we have done is we've essentially found the inverse function. We had y equals, and we solved for x. If we switch these x's and y's, we'll have finished finding the inverse function. So this is essentially what it looks like to find an inverse of a trig function. Next question. Practically the same one. Solve for x. So we'll start by adding 1 to get y equals, let's try that again. Y plus 1 equals 3 tangent 2x. Divide by the 3. Cancel, cancel. We have y plus 1 over 3 equals, I'm leaving a little space in front of the tangent because I know an arctangent's coming. Gives me a little room to write it. Arctangent negative 1, with some parentheses, will cancel the tangent out. We're getting closer now. We have arctangent of y plus 1 over 3 equals 2x. Since I already have fractions in my problem right here, I don't want to divide by 2, so instead I'm going to multiply by 1/2. It just keeps it a little bit cleaner. And I'm going to write x now. X equals 1/2 arctangent of y plus 1 over 3. That completes this question. Next question. Alright, now we get to actually find the inverse of a function. State the domain and range of the inverse function. In order to get the domain and range of the inverse function, it's helpful to have the domain and range of the start function. They give us the domain, negative pi sixths, less than or equal to x, less than or equal to pi sixths. If you were to look at the graph of 5 sine 3x on that domain, you would recognize that on that domain the function is a 1-to-1 function, meaning its inverse will also be a function. That's why they restricted the domain. Usually sine has the full up and down, up and down, up and down, but you'll find that when they do these restrictions, it gives you just the piece that its inverse will be a function. And that's going to take forever. There we go. So, let's get the domain. Let's get the range. The range of sine is from here to here. In general. Now you can push this up and down if you have a plus number, but in our case we don't have a big plus 5 or something here. We do have a 5 times. That affects the amplitude. So in our case this would be 5 and this would be negative 5. So our domain, given our range, would be negative 5 less than or equal to y less than or equal to 5. Less than or equal looks kind of sad. There we go. That is going to be our range. Let me redraw this. Okay, so we have -5 less than or equal to y less than or equal to 5. So we have our domain and range of the original one. The concept of solving for an inverse function is switch x and y. So this is now going to be x equals 5 sine 3y, and solve for y. When you switch x and y, you also get your old domain switching x and y. It's now the range. And your old domain on your old range, switching x and y, is now your new domain. So we already have our range and domain for the new inverse function, although we haven't found the inverse function yet. We have the old domain and range, so that switches to the new range and domain. Now, going back to our function, we've switched x's and y's. Now we start solving for y. We have x over 5 equals sine of 3y. We take arc sine of both sides, and we have arc sine of x over 5 equals 3y, and we divide by 3, and we have y. We can now write f inverse of x equals 1/3 arc sine of x over 5 comma -pi6. Or let's do this one in the opposite order. Let's do domain first. Now I'm just copying these down. We've already worked them out. No thought needed. -5 less than or equal to x less than or equal to 5, and -pi6 less than or equal to y less than or equal to pi6. We have found the inverse of the function and stated its domain and range. Great, next question. Find all real numbers that satisfy the equation, all real numbers, and approximate to 2 decimal places. Now they don't specify degrees or radians, so this one we get to choose. Just make sure you know what mode you're in. Starting, though, we have to solve for sine. So that would, subtracting 2 would be a good step to begin. That would be 3 equals 5 sine x. Then we can divide by 5, and we have 3/5 equals sine x. Then we can take arc sine to solve for x. We have x equals arc sine of 3/5. But, arc sine, before that, we had sine x equals 3/5. Where is sine positive? Sine's positive here and here. But we want all real numbers, so we're going to have a plus 2k pi kind of an answer. Let's go degrees this time because I haven't done a plus. Oh wait, we did one. It doesn't matter. I said degrees. Let's do degrees. Round to 2 decimal places. So we go to our calculator, making sure we're in degree mode, and do arc sine of 3/5. 2 decimal places. I get out of this 36.869, so 87. That's this answer. We can take that and add 360 degrees K and get all of those. That one and that one and that one and that one forevermore. But we also need this one. Now that is going to be 180 minus 36 0.87. Doing that on our calculator, we get 143.13. So we also have 143.13, and we need all real solutions. Because we need all real solutions, we need to do this one on every one of them. Now I realize I forgot a degree symbol on our previous, and here's a degree symbol. And that one's also going to be 360K. And that will get this answer, and this answer, and this answer forevermore. Okay, that completes this section.